Cool. All right. So we've been talking, whoops, not about cities, about aldehydes and ketones, and in particular, we learned about this class of reaction, these nucleophilic addition reactions. All right, so based on what we learned last time, let's just kind of summarize a few of these. I'm going to put an aldehyde or ketone in the middle of the page here. Okay, and we're going to make this little wheel of all the different reactions that we know, not all of them, but a lot of the different reactions that we know how to do. All right, so first of all, we talked about what you would get if you treated your, in this case, it's what? An aldehyde or a ketone? An aldehyde with a Grignard reagent. That was actually review from the previous chapter. All right, we also talked about other nucleophiles that we could use. Okay, so to be clear, you're going to be filling in these products here. Okay, so all of these are considered nucleophilic addition reactions, right? So we're adding our nucleophile. All these are nucleophiles to this aldehyde here. And specifically, where is the electrophilic site on this aldehyde that we're going to add to? The carbonyl carbon. This guy right here, right? That's where my new bond was going to be. So in each of these nucleophiles, I want to identify my nucleophilic site. Where's that new bond going to be? For the Grignard, it's that carbon that's attached to your metal, to that magnesium. So I'm going to start by redrawing those 4 carbons of my aldehyde. And I get to this blue one here. Since that used to be my carbonyl carbon, I know that when I draw this new bond, on the other side has to be that red carbon, right? My nucleophilic carbon. Cool, so then I'm just going to make sure to include the rest of what was in that Grignard, which was just one more additional carbon. All right, to be clear, these 2 here were what were in my Grignard, and these here are what were in my aldehyde. And then I'm done. What else do I need to include in my product? That OH, right? So, although we no longer have a carbon-oxygen double bond, that oxygen is still there. Now we just have a carbon-oxygen single bond or an alcohol group. All right, that's why we studied that reaction in that alcohols chapter. Okay? And that's going to be true for all of our products. We don't lose that carbonyl oxygen, but it does become a hydroxyl group, a carbon-oxygen single bond instead of a carbon-oxygen double bond. Cool. All right, so now I'm going to treat it with this thing here, this oxygen with a negative charge. We call an alkoxide ion. And importantly, that negatively charged oxygen is that nucleophilic site. That's got all that electron density. So that's what's going to attack that electrophile. So again, I'm going to start by redrawing my 4 carbons from my aldehyde. I get to my carbonyl carbon here, so when I draw my new bond, let me make some room for myself. On the other side of that new bond has to be that nucleophilic oxygen. Okay, it still has those 2 carbons on there. Right, these 2 here from my nucleophile. Okay, and now just focusing on this red oxygen for a second. It was negatively charged as my nucleophile. What's the charge going to be when I add it? Neutral, right? It's going to lose that negative charge. To be clear, this pair of electrons right here, actually you could choose any one of them, but one of those pairs of electrons is now going to be used to create your new bond, right? So now my oxygen just has 2 lone pairs, and an oxygen with 2 bonds and 2 lone pairs is neutral. And just like we said before, we're going to be good and make sure to include that orange oxygen as well, but it's no longer a carbon-oxygen double bond, but a carbon-oxygen single bond. Okay. Now I'm going to use not a negatively charged alkoxide ion, but an alcohol, all right? I'm going to have to do this under acidic conditions instead of basic conditions, but what's the difference between the product that I get down here and up here? There is no difference for this particular chapter. Previously, we had to distinguish between acidic nucleophiles and basic nucleophiles because it depended on which carbon was going to be attacked. We only got one possible electrophilic site in an aldehyde or ketone. So my oxygen is going to do the same thing it's going to attack, but since it's a neutral nucleophile, it's going to lose a hydrogen in the process, and I will get the exact same product, right? So whether I choose that basic nucleophile or its equivalent acidic nucleophile, I'm going to get the same product for aldehydes and ketones because we only got one electrophilic site. All right, one thing maybe we should make note for this example, as we said, our neutral nucleophiles, they always lose a hydrogen. All right, and then lastly, we have this example here. This is now this cyanide ion. Which one of these two atoms is my my nucleophilic site? Okay, this is important. It is always going to be that carbon atom. That's the one with the pair of electrons. And you got to be careful because sometimes we abbreviate this as just Cn-, and you got to know what that is, right? That is that cyanide ion. If we draw its full Lewis structure, that's our structure here, okay? We're going to do the same thing. We're going to draw our 4 carbons. We get to that electrophilic site. I'm going to draw my new bond. On the other side must be that carbon from my cyanide ion, my nucleophile. And remember, I'm going to be really good because this is a triple bond. I'm not going to draw a kink. I'm going to draw this linear structure here. Boom. Right, and actually let me move my red dot. There's where that red carbon is. Right, remember those triple bonds, we got to be linear about those bonds. Okay, if you did draw kinks, that would be worth a heck of a lot of extra credit, but you would definitely lose a point for not drawing that triple bond correctly. All right? Did I say extra credit, partial credit? I don't remember what I said. A heck of a lot, not extra credit. Heck of a lot of partial credit, and then you would get a point off because you didn't draw it correctly. Okay. Cool. And then we're going to include that OH on that blue carbon as well. Okay? So this is just kind of a little bit of a summary of these nucleophilic addition reactions that we learned with aldehydes and ketones using various nucleophilic sites. In this case, they were all either carbons and oxygens. Another one that we saw last class doing an example of was sulfurs. There's one particular atom that we've kind of left out of here. I've conveniently kind of skipped over, and we haven't seen it in this particular chapter, but we saw it before. And that's because we're going to put it in a different category in our brains here. These are our nitrogen nucleophiles. All right, this is one way in which these nucleophilic addition reactions really differ between aldehydes and ketones and our epoxides that we studied last chapter. Okay, so first of all, let's just do an example here. Here's a ketone. We'll take our simplest ketone, acetone. I'm going to put in a nitrogen nucleophile. We'll use ammonia here. And I want everybody to just predict what you think would happen based on what we've studied up until this point. So of course my electrophilic site is that carbonyl carbon. All right, my nucleophile here, what's my nucleophilic site? The hydrogen or the nitrogen? It's got to be something with some electrons, right? So that lone pair on that nitrogen gives it away. That's going to be my nucleophilic site. And since this is neutral, what am I going to do when I add it? I'm going to lose a hydrogen. All All right, so I got this new bond between my electrophile and my nucleophile, just like always. All right, and then what else am I going to put on that blue carbon? An OH. Cool. So this is what you would expect to happen based on every other nucleophilic addition reaction that we've learned. All right, and this does indeed occur. But the problem is it doesn't stop there. This is an unstable intermediate. So there's more to the story here. We would get a different product. This thing is going to continue to kind of rearrange itself and give us a new product. All right, and so that's what we're trying to figure out here is what happens with our nitrogen nucleophiles. Okay, before we go on, we got to talk about nitrogen nucleophiles real quickly. It's important that we classify these compounds. We've talked about classifying carbons and alcohols and alkyl halides. Now we need to talk about classifying amines. All right, these are our nitrogen-containing functional groups here. So the simplest one, which technically isn't even an organic molecule because there's no carbons in it, is what's called ammonia. Okay, ammonia's, you may have heard back when I was a kid, they used it as a cleaning product. I feel like it's not as popular anymore, but maybe you've seen it. It's also a really important molecule in biology. It turns out that an important part of our biological process is creating ammonia, but it's toxic for us, so our body has a way of like cleaning it up, blah, blah, blah. You may have been introduced to this molecule before. This is our simplest amine. All right, if we have carbons on there, we can have what's called a primary amine. All right, meaning that that nitrogen is bound to just one carbon. All right, we can also have a secondary amine. And this is where things are a little bit different than when we talked about alcohols. Alcohols necessarily contained an OH group. So there is only one possible bond that you could create. Nitrogen can create a whole bunch of bonds. So when we talk about a secondary amine, we're not looking at the carbon, we're looking at the nitrogen itself and counting how many carbons it's bound to. Right? So a primary amine is because the nitrogen is bound to just one carbon. A secondary amine is when the nitrogen is bound to two carbons. So I want you all to take a second and see if you can't predict what a tertiary amine will look like based on this pattern here. Okay, so how many carbons should that nitrogen be bound to? 3. All right, and notice each time I'm kind of taking off one of those hydrogens and replacing it with a carbon. So whereas ammonia has 3 hydrogens, a primary amine only has 2 hydrogens, a secondary amine has 1 hydrogen, and a tertiary amine doesn't have any because they're all replaced with carbons. Now, I chose these 2 carbon groups, these ethyl groups coming off. It doesn't have to be 2 carbons. It could be 4, 1, whatever, right? I mean, there's just some number of carbons connected to that nitrogen in our amines. Okay, cool. So this is going to be important because we're going to see a different product depending on what amine we choose here. All right, so for our nitrogen nucleophiles, we're going to have to distinguish between what happens with primary amines. All right, we'll take our simplest ketone again, could have any aldehyde or ketone. And now we're going to take that primary amine. All right, what we would expect to happen is to form this compound here where the oxygen and the nitrogen are both attached to that same carbon. All right, but again, this is our unstable intermediate. So it doesn't stop here. It's going to keep on reacting, and that nitrogen's actually going to fight and kick off that OH group. All right, and what we're going to create is now a carbon-nitrogen double bond. This is a molecule we call not an amine with an A, but an imine with an I. Just flip this around. Okay. So we have no oxygen in this product. This oxygen's been just completely kind of kicked off here. If we really wanted to do a balanced chemical equation, water would be another product here. That's where my oxygen went off to and my missing hydrogens. All right, but again, we don't really care about the inorganic product. I only care about this imine product. All right, and if we notice, what I did was I kind of just picked up this amine here. Whoops, let me get its lone pairs on there. And I use that to completely replace the oxygen on that compound, right? I now have an oxygen-carbon double bond, a carbon-nitrogen double bond with the remaining 2 carbons on that nitrogen chain, right, on that amine. So that's my imine product that I get when I use a primary amine. We'll take this same ketone. And now we need to talk about what happens when we use a secondary amine. Okay, again, we would sort of expect to just have that neutral nucleophile lose a carbon. And to retain that OH group. But again, this is our unstable intermediate. right? Again, nitrogen and oxygen, when they're on the same carbon, they kind of fight, all right? Previously, how many hydrogens did our amine lose in order to become our imine? 2, right? Down here, I can't do the same thing. I only have 1 hydrogen on this secondary amine, so I'm not going to get this same imine product, but it is, again, going to fight and kick that oxygen off. All right, when that oxygen leaves, it's going to take a hydrogen from a neighboring carbon, leaving me with a carbon-carbon double bond and my nitrogen attached to that formerly carbonyl group, carbonyl carbon rather. All right, so instead of an imine, we get what's called an ene for that double bond, that carbon-carbon double bond, an ene-amine product. All right, again, ene because we get this carbon-carbon double bond, and amine because we have that amine group on there. All right, and then lastly, if I have a tertiary amine, all right, what is our rule for neutral nucleophiles? How do we add them? What do we got to do when we have a neutral nucleophile? What did we say before? It's got to lose a hydrogen, okay? We look at our tertiary amine. What's the problem? It doesn't have a hydrogen. All right, so it turns out tertiary amines, they can't be nucleophiles because they don't have that hydrogen to lose, so we don't get any product reacting a tertiary amine with an aldehyde or ketone.
Nice.
Yeah, best case scenario. Okay, cool. So primary amines, we get this really weird, we like, in terms of if you shrunk down in your magic school bus and you were looking at what happened, at first, everything goes exactly according to plan. You get this intermediate that you would expect, but it doesn't stop there. Your nitrogen and your oxygen on the same carbon, they start fighting, and the nitrogen wins and kicks it off. So with a primary amine, you get this carbon-nitrogen double bond, what we call an imine. When you have a secondary amine, you can't possibly get a carbon-nitrogen double bond because there's not another hydrogen. So instead, when that oxygen leaves, it steals a hydrogen from a neighboring carbon, giving you an enamine. All right, so we get these really weird products with our nitrogen nucleophiles. Again, we kind of like talked about nucleophiles in general, and then we're making this little subcategory for our nitrogen nucleophiles because they don't exactly behave the same, all right? And within that subcategory, we're going to distinguish between primary amines, which give us our imines, and secondary amines, which give us our enamines. All right, so let's just sort of create a new little wheel here. What's up?
So on the secondary,
Yeah.
amine, at the very end, does it matter which side your double bond would go to, depending if like you had like a more complicated model?
Yeah. So let's do an example here, and we'll try to reason between what that would be. All right. So let's just put a random ketone in the middle here. All right, and on one side, we're going to react it with a primary amine. Again, we'll make it a little bit more ugly and complicated here. And on the other side, we'll react it with a secondary amine. All right, so I'm going to rearrange this a little bit to give myself a little bit more room. All right, cool. So, importantly, that's the one thing that is consistent is that this nucleophilic site, these nitrogens are going to be attached to my electrophilic site on my aldehyde, or in this case, ketone. All right. For my primary amine, I'm just going to pick up this nucleophile right here. And I'm going to put it on right where that oxygen used to be. All right, so now I have my nitrogen. It's still got those 3 carbons attached to it, but now it's replaced the oxygen and is double bonded to that carbonyl carbon, or what used to be a carbonyl carbon. If I try to do the same thing over here, all right, pick up that secondary amine and replace it. I can't do that without breaking nitrogen's octet, right? So I'm not going to get this carbon-nitrogen single bond. I'm going to get a I'm not going to get a carbon-nitrogen double bond. I'm going to get a carbon-nitrogen single bond. All right, but there is going to be a double bond in here. It'll just be a carbon-carbon double bond. So let's draw our 2 possibilities and see if we can't figure out which one should be our product here, all right? I have 2 neighboring carbons, so I can either have this one over here on the right, or I can have, that's not the right, sorry. I don't really know my right from left too bad. On the left, all right, and the other one will have the double bond formed on the right. So which one of these do we think would be our major product of this reaction here, left or right? Why right? More substituted alkene, right? We want that more substituted is more stable, lower energy product, okay? So in terms of the carbon that's more likely to give up its hydrogen, we want to form that more substituted double bond. All right, and previously I had made you with all of our elimination reactions. Draw me all possible products and give me tell me what was major and minor. In this case, I'm just going to ask you for the major product of these reactions. So you want to give me the more substituted alkene for your enamine. All right. That is the other thing that I want you guys to know here is the name of these two bizarre functional groups that we really don't see too often are imines. And again, are enamines. Okay, both of these turn out to play important roles biologically. You do see them come up in biochemistry. So yeah, we just want to sort of make note and have that in our vocabulary. Okay, cool. So we talked about these nucleophilic addition reactions of aldehydes and ketones. All right, where we're going to attach that nucleophile to that electrophilic carbonyl carbon, right? That's the phrase you want to have down in your head, electrophilic carbonyl carbon. If we have a negatively charged nucleophile, we just kind of attach it and it becomes neutral. If we have a neutral nucleophile, we're going to have to remove a hydrogen so it remains neutral when it attaches. All right, and then we introduce this problem here with our nitrogen nucleophiles. These form a little bit different of products here. Primary amines form those enamines, whereas primary amines form, primary amines form those imines, and secondary amines form those enamines, whereas tertiary amines, they can't play the role of nucleophiles because they don't have any hydrogen to lose, so you don't get any product at all, all right? And then last sort of complication I can throw at you here is what if we have a more complicated aldehyde or ketone? What is my enamine product? Well, just like before, we want our alkene to be that most stable, aka most substituted double bond, carbon-carbon double bond. All right, that's all I got for y'all. Cool. Break. Enjoy.
Nice.
Yeah.